All right. So as the clock turns to 1 Eastern time, let's start today's tutorial lecture. So this is the third lecture out of our 8-lecture series on the practical guide to building superconducting qubit experiments. So today, it's our great pleasure to have Wei Dai from Yale to give us this lecture on finite element modeling and device design. So Wei Dai is a graduate student in Michelle Deveray's lab at Yale. So he will have a lot of hands-on experience with this material to share with you guys. And so now the stage is yours, Wei.
Yeah, thanks, Chen. And hello, everyone. So my name is Wei Dai. I'm currently 5th year PhD student. So just now I already flashed through this syllabus, I think. So in the previous 2 talks, I believe you, Steve and Jens, have talked about just general idea of superconducting qubits and quantization of circuits, basically. And this, compared to the previous 2, is a very technical talk that deals with a very specific task in our job. So this is my idea of the general workflow in our lab or in any like superconducting quantum circuit lab, that you start with an idea for an experiment, but as experimentalists, we have to narrow down to a target Hamiltonian that we're going to engineer to realize that idea. And then we design a circuit to achieve that Hamiltonian. And then we have to do circuit analysis or electromagnetic analysis to see whether this design gives us our target Hamiltonian or not. And this is actually going to be the task that we are tackling in this talk today. So if we finally get the Hamiltonian we want, then okay, good. We fabricate the device and start doing experiment in the fridge. But most of the time, this process takes several iterations that you will need to update the design until you converge to your desired Hamiltonian. So essentially, what we want is a Hamiltonian that, sorry, there's a failure in the animation, but okay. So in the previous talk, I believe what you learned is when you start with an LC circuit that looks like this, LCJ circuit that looks like this, then you know how to write down the Hamiltonian of such a system. Eventually, something that looks like this. But this is usually not what we are targeted for, right? So for example, what we usually want in this system, we call it a qubit coupling to a LC resonator. What we eventually want is, say, a dispersive Hamiltonian that looks like this. Well, this in specific is a transmon qubit, which I hope you remember that it's an harmonic oscillator, which looks like a harmonic oscillator with such a Kerr term. And we have a linear harmonic oscillator, which is the cavity, and there's the dispersive coupling, which is effectively a ZZ interaction between these. So how do we usually go from such a circuit Hamiltonian formed by LCJ circuit and dynamical variables of phi and q to a Hamiltonian that looks like this? Yeah. And more importantly, even this LC circuit in our actual experiment is not an actual thing. So in the lab, we don't have such component as lumped capacitance and inductance that we build circuits on, because at microwave frequency, all the wavelengths are actually comparable to our actual package. So this is the regime where we say all the package falls in the distributed element regime, which is none of the elements is actually much smaller compared to the wavelength. So we have to think of the entire media, the entire metal, as the circuit. And we synthesize the entire package of the device. So eventually this design that we usually model as this LC model, in lab, it probably actually looks like this. So it's this thing, we call it a lumped over 2 resonator, capacitively coupled to a Cooper pair box transmon, actually. So then the question that we're going to tackle in this talk is, how do we get our target Hamiltonian that look like this, for example, from the actual design instead of from the LC circuit? And moreover, so yeah, this is what you will find in papers that how actual superconducting circuit might look like. Or if you are familiar with the 3D transmon, what we call superconducting circuit might even look funnier, that actually by a 3D cavity that look like this, or like this, two cavity with like a qubit coupling with another resonator on chip. Or if you are more familiar with the 2D stuff, then even in that case, the cavities or qubits, etc., actually have such kind of geometry. So how do we go from the actual layout of the device to a Hamiltonian? And we do it by the full electromagnetic analysis, which we do with a software called HFSS. So that is going to be the main part of today's talk. So in this talk, we are going to first introduce HFSS with two examples that I will to demonstrate. And then, oh, sorry. Yeah, sorry. Okay, sorry guys, yeah. So with introduction to HFSS, and then we're going to answer a question that what do we as circuit QED experimentalists, what do we ask from HFSS? Is there any specific things we do with HFSS that is different from the classical microwave engineer, let's say, which in particular is how to deal with Josephson junction in such simulation, and a trick called black box quantization, and a Python package called PyEPR. Yeah, and these are going to be mostly on the slides. And then I'll go into a demo in HFSS to show you basically how do we set up a simulation and how do we generally set in the software and the workflow that actually do the analysis. So okay, so I hope, yeah, okay, then I'll just go into the content. HFSS stands for High Frequency Structure Simulator. So it is a software that does a 3D electromagnetic simulation with a finite element method that basically solves Maxwell equation in frequency domain. So HFSS is part of the ANSYS suite, which is compatible with some of other packages that ANSYS provides, like Maxwell, that for example. So if you heard of ANSYS, that HFSS itself is very widely used in the classical microwave engineering that people use for antenna design and packaging PCB design, or simulating connectors of etc. So if you think of it, our transmon, like two pads with an inductor, it's actually kind of an antenna, right? So it actually makes sense that we use HFSS in a similar manner as the antenna engineers do. Disclaimer, so HFSS is actually a commercial software, and I don't want to give you the impression that we are advertising for them. So the goal is just to do electromagnetic simulation, to do analysis of the 3D package. And there are other tools that can do this. For example, Axiom, which is compatible to Microwave Office, actually. That's another very handy tool. Or Sonnet. So both Axiom and Sonnet are specialized to do 2D, or the so-called 2.5D structure simulation, which is you can have multiple of 2D structures. So if you are dealing with that system specifically, sometimes it's more handy to use Axiom or Sonnet instead of HFSS. HFSS is just a more sophisticated and a more complete tool. And apart from that, there are CST that basically does the same thing as HFSS, solves it slightly differently. So CST is more specializing if you're doing transient time domain simulation. Yeah, or COMSO, if you've heard of, I think it's a more famous finite element method that can do both electromagnetic simulation along with some other, say, stress or thermodynamical simulation that you can see the motive physics or, for example, piezoelectric effect on. Yeah, but just today we are going to focus mainly on HFSS. But again, you can do what we want to do with all these other softwares as well, if you want. So what does HFSS do really? As I just said, it basically just solves Maxwell equation given certain boundary condition that we define in the software. That's the structure. So in finite element method, basically the whole idea is to divide the whole region that we see to many small and simple shape called elements. And this division is called a mesh. And the E and B field are approximate within each element from solving difference equations. And the key point is—
excuse me. Hi, wait,
sorry.
just to interrupt a little bit. There's a question, why is HFSS more frequently used than the other softwares? Just in light of comparing with other packages you just mentioned, I'm not sure if this is true though. So do you have any comments on do you feel like HFSS is more frequently used in our field than others, or what are the pros and cons? Do you have any thoughts?
Yeah, thanks for the question. Yeah, in my experience, I would say I do use HFSS most frequently. And I think the main reason is we have Python packages that is compatible with HFSS like this. There's PyHFSS package that allows import and output from the HFSS software into Python. And there's PyEPR that I'm going to talk about later. But as I said, so if you're doing mainly with 2D stuff, then sometimes I feel Axiom or Sonnet is also widely used as well. So apart from that, I won't say HFSS is really better in terms of precision or anything compared to these. Yeah.
Okay, thanks.
Yeah. Thanks. Yeah. So where are I? Yeah. Finite element method solving Maxwell equation by just getting electric and magnetic field within each element, and then make sure that the fields are continuous across the boundaries of elements, which then constitutes the overall solution. So basically, that gives us an idea of what we want to do in HFS. It's actually 3 separate tasks. One is CAD, or computer-assisted design, is drawing the structure, basically, as you would make for machining. And then to set the meshing, which is the key step for finite element method, and then solve the electromagnetic problem. Well, what we need to do is to provide a boundary condition, electromagnetic boundary condition, etc. So HFSS is a very complicated tool, but I think it's always a good idea to keep these 3 categories in mind. And for whatever you do, think of what am I doing in terms of these 3 categories. So as I said, meshing is the trickiest, I would say, part and the most important step in finite element method. I'm no expert of finite element analysis, but the point is you don't have to be an expert to use HFSS. And it does the meshing in a very smart way, and that's mostly what we're paying it for. So the mesh it does is called a conformal meshing, which is basically a type of meshing that makes sure it tiles any surface with triangle, for example, that make sure the boundary conform to the boundaries of the regions. Say this is region 1 and region 2, labeled in different color, has different boundary condition, then it will mesh the surface in this way, such that the boundary is looks like this. And in a 3D environment, for example, it's instead of triangle, it will do this tetrahedron that fill up the whole 3D surface. So, and importantly, HFSS does the meshing in a smart way. That's called adaptive meshing, which is it only starts with a very coarse mesh, and then it automatically modify the mesh by itself as it's running, as it's analyzing, to minimize the field gradient or to minimize error, basically. And what the user give is only a seed for the meshing or the initial meshing, and then it will start doing the analysis and then refine the mesh from pass to pass. It refines the mesh at where the solution changes from path to path until it converges, until it's no longer changing. And then that gives the final solution. So this adaptive meshing process is very, very powerful. That basically we don't need to do it. We don't need to provide the exact meshing. It will basically find the correct meshing that gives you the final result. However, it doesn't mean that we can just not care about the meshing process at all. So as I will introduce in the following examples, it's still very important to give the correct initial meshing so that it captures the effect that we care about in a efficient way, or so that it doesn't take too much memories, etc. So, or it converges faster. One comment before we go into the actual example is HFSS is very memory consuming, I would say. So I would not recommend you install that on your laptop. But I mean, is there other questions that I?
Well, so I think it's fine for you to go forward. You don't have to pay attention
Okay, sorry,
to the question panel. I will interrupt you and convey any questions.
Thanks, Chen. Yes. So given that, I hope that's basically all I want to talk about HFSS, and I think it's more useful, more helpful to just go to that software to show you how it looks like. But before we actually go, I want to do just two very simple examples. But to keep us on the same page, when we simulate, we want to simulate something that we understand, just to start with, to make sure we get the software correctly by comparing with something I already know. So the first example I will do is rectangular cavity, which I know the standing mode of this cavity is going to be something that looks like this. Well, the TE110 mode defined this way would be m = 1, n = 1. So I want to see whether HFSS give me that eigenmode. Yeah. And the second example is I want to simulate a coaxial transmission line. That if you're not familiar with microwave engineering, so the coaxial transmission line is basically a structure like this, where we have an outer conductor and an inner conductor, and the E field has a feature like this. This is a cross section of the transmission line. So it's a TEM mode as it propagates through the transmission line. And I'm going to simulate how it, so the transmission property or the S parameter of that as an example. So I hope these are not. So now let me try to share screen. Now, do you see a very intimidating window? I hope you are seeing share screen. Oh, good. Yeah, it's a little tricky because I'm sharing on remote desktop, but okay. So I have created,
which is currently running a simulation. Okay.
Yeah, yeah, yeah. This is I have made this practice job, and actually I've ran the simulation beforehand, but just right now I want to eat everything and show you how I actually make the design. So we usually start from scratch. That's something like this. Okay, before we go into the actual design, let me introduce what this overall thing it is. It's from first glance, it might be quite intimidating. It has a lot of options and different menus that way more than what we usually need to do. But so there's this project manager that shows you the project that we're currently working on and designs in it. And then there's this properties that's for each design. For example, we have design parameters. That's yeah, I'm going to show you right away. There's the message manager that usually you see from just when it arrow pop up, and progress is when it's running a simulation. Like now, it will show you how that simulation is going. And this is the canvas that actually will make the design and see how the geometry look like. So now the first example is we want to start simulating. How should I hide this? Say a rectangular cavity. This is a very intuitive way to make the drawing. I would say the same way as you do in any CAD software. If you have used SolidWorks or AutoCAD, then basically you do it the same way as these options. And it's a good habit. I consider it a good habit to parameterize the design in, for example, so this gives us basically a rectangular cavity, X, Y, Z dimensions. And I would call X dimension A, which is the parameter I have previously designed in the job. And the Y size being B, Z size being C, for example. So if I want to center it at 0, then I put it here. So for a rectangle, it defines the position starting from one vertex of that box. And when I do it this way, you'll see it's a box that looks like this. So you can view the variables I designed in here. So project properties, or in this setting, it's actually just show it in here. And the advantage of parameterized design is now it's very easy to simply say, change the design just in here, instead of going into the design and change everything. And more importantly, when you have multiple things stacked together, sometimes you want some things to be changing along with each other, then this is the neatest way to do it. So now, this is the CAD part, just the easiest example. And now I want to run an eigenmode simulation. I want to simulate the eigenmodes of this box. We're saying that HFSS has different solution type, that it can do either driven model. So this default HFSS class is called driven simulation, which is simulating the response function from driven ports, that it can do either modal driven simulation or the terminal driven simulation. The difference between these two are not there's basically not too much difference between these two. Well, we usually use driven model that converges on the S parameter or scattering parameter of the matrix, but driven terminal solves it in terms of voltage and current instead of the power scattering parameter. But for most of our application, I would say it should have no difference. But for some historical reason, we use driven model more than we use driven terminal. But for now, for this simulation we want to run, we just want to do the eigenmode simulation, solution type eigenmode. That it just gives the eigenmode of the system, which we can set in analysis. So I apologize. This is copied from something that I previously made. So, but when you want to start everything from scratch, it actually looks like this. And you can define a job by adding a solution setup. Now it's has a panel like this. So I want to simulate, say, 5 eigenmodes that is higher than 3 gigahertz. This is what this means. And I want you to run with a maximum number of passes 15, or a maximum delta frequency that is, say, 0.5%. So what this means is it will eat the adaptive meshing and refine. I have been disconnected. Uh-oh. No, this is embarrassing. Yeah, this is what I fear the most about sharing desktop, sharing remote desktop. No, but I'm doing the correct thing. I reserved for this session, so whoever kicked me out is not being a good person. Anyway, I should go on. So what this does is the adaptive meshing as it goes from run to run would stop either when it reaches 15 rounds, or that it has converges by less than 0.5% deviation from run to run. Yeah. How should I hide this? Yeah, it's a little annoying that. Would it be better if I put it here? Okay. another good practice to do is the minimal number of rounds. So what this means is, here I only specify when do I want it to stop. But what if it just give me a good convergence just from the second run? So I also wanted to run a few more than that to just make sure the convergence is real, it's actually happening. So I commanded you. So even if you have converged within 0.5% in the second round, I ask you to run a minimal amount of 3 rounds just to make sure that the convergence is real. And the order of basis function you can do. To be honest, I don't know exactly what this really means, but the way I learned it is people told me it's better to do the mixed order. So I'll do it this way. And this created a setup in the analysis. So now, if I run it, it should start doing the analysis. Okay, for now, I'll just stop this previous job for whatsoever. There's another handy tool in HFSS that is called validation check. So when you open this, it's basically, there's a checklist that tells you whether you have defined everything correctly or not. So what we have done is we made the CAD drawing of the design, and we have defined the analysis setup, but we have done nothing about the electromagnetic boundary condition, right? And why it says it's done. That's because the default setting in HFSS is when you create a box, a 3D object. Now this box itself, the material for this box is by default vacuum. And then outside the box, this external boundary of it is by default perfect E boundary condition, or perfect E is essentially like superconductor, you can think of it. So the default setting in HFSS basically make it, when you make a 3D object like this, it's as if it's an empty cavity enveloped by superconductor. So this is the 3D box that we want to simulate, basically. So another thing that we haven't done is the mesh. We have not given it the initial mesh. So now what it does is HFSS will just assign the initial mass with a fraction of like the actual dimension of the box. But it might be better to give it apply mesh operation, assign mesh operation inside the selection, where I have select the object, so length space. This means I want the initial mesh within this object, this box, to be no larger than 4 millimeter. When I give this, this will pop up in the mesh conditioning here. So now if I analyze the job, yeah, that box, because there is a previous job running and it's not able to save the setting before it runs the simulation, which is usually not a good thing to do, but no, I think I know what I'm doing, so I believe this is fine.
Okay, wait. So at this point, maybe just let's address a few questions related to what you discussed. So one is you have parameterized this design with this ABC. So there are people wondering, can you import some geometries from outside, from some CAD model, maybe some other software into HFSS, and then define parameters that can be varied in the simulation? Do you know of interfacing tools like that, or do you just to hand draw geometry? That's the only way to parameterize.
Good question. So we can import from external job, like you can import a GDS file into HFSS, for example. I don't know how you can import like a 3D CAD design, but I think HFSS doesn't work, like the parameterize doesn't work when you import. So when you import an object, it has like, it's basically one whole object here defined like a point-wise feature. So there might be a smart way to convert that into like the intrinsic objects built from HFSS, but the easy way to parameterize the design is to make all the design in here. So eventually you have a CAD software that you are most familiar with. And when you do enough simulation with HFSS, this becomes your most comfortable CAD drawing software. So like in our actual experiment, the cavity, for example, that looked like this, I made all the design in HFSS and export this actually. So that's only because it's easy to parameterize it inside HFSS. So yeah,
Okay.
I
So
hope
another,
HFSS has more support for importing, but
so
unfortunately
another question is on meshing. So how much resolution do you typically ask for in meshing? And the example given is if your feature size is say 10 micron, how many mesh points do you have within that? And yeah, do you have a rule of thumb of how do you set the initial meshing?
Yeah, that's another good question. So that's what I'm planning to show you right away. So for this example, it's just a box mode cavity. So I know exactly what the mode should be, and I think just meshing like this fine should be able to capture the eigenmodes of this box very faithfully. So I ask it to start with no larger than 4 millimeter in the mesh size, and this is no mesh it converge to. So we can look at, so this simulation is done. We can look at the result from right click, you can view it from solution data, and this is the first 5 eigenmodes of this box, which I happen to know that it's roughly the number I expect. If you do the math like with a pencil paper, then you should see that with our dimensions, this is roughly the modes. It's always a good habit to look at the convergence, to look at how it solves the eigenmodes from run to run. So it starts with say 5,600 elements. That is according to my initial mesh, and then it refines it again until it converges when it has 10,000 elements like this, and it converges with a relative difference of 0.009% compared to the previous round. So this convergence, to emphasize, this convergence doesn't mean that it gives you the correct answer within that precision. It only tells you that it converges compared to its previous round with this much of deviation. So that means the HFSS itself, the meshing itself, is not causing numeric error that is larger than this. But there's still a chance that even this number could still be off from the physical parameter if your setting is wrong. So just when you see such a small delta frequency, do not think of, yeah, this is super precise with this precision. Because if you think that way, then in the actual experiment, you might be surprised to find that your frequency is still a little off compared to your simulated frequency. Because in some sense, how good do you have control in like the parameters like this? So you don't have precise control with higher precision than your caliper, right? And when you cool something down, for example, the dimension of any 3D cavity of any geometry might have thermal shrink. So it's very common to have deviation from the simulated value due to that kind of reasons. But the thing we want to make sure in simulation is that it's not giving us numeric error due to the meshing itself or due to your mistake in setting up the simulation. So now what we have seen is, yeah, it basically finds the correct eigenmodes frequency, if you verify that, with pretty good convergence for the numeric error itself. But if you're being careful enough, and I suggest you do it, is you can change the initial condition. Now I changed the initial meshing. Okay, you can't do it here because the way HFSS works is when it has run the simulation, it will remember this final mesh. And then when you run something again, when you create another, when you modify this setting and run it again, it will remember this mesh that it created from the previous job. But if you start from scratch, make the same design and give it a different initial meshing seed, then in principle, that should have no influence on the final result it converged to, right? Because the initial meshing should not matter for the electromagnetic solution. But if you see that it actually converged to slightly different value, then you know there's something you have done wrong. So a practice I suggest you do when you actually play with HFSS. But yeah, I'm just not planning to show you all of these now for the sake of time. So this is one example. eigenmode simulation in HFSS. I hope you get the rough idea of how the software works. And,
so there's a question on how do you model superconductors, especially the Meissner effect in the software?
Yeah. Thanks. Yeah, so I said something wrong just now. I said that perfect E is essentially a superconducting boundary condition, which is not correct because a superconductor is not only perfect E, but also a perfect Meissner effect, that magnetic field repulsion. So how do I model that? Good question. I don't really know. So we don't usually model. We usually model superconductor just as perfect E boundary condition, right? So because kind of in microwave frequency, the electric field and magnetic field are like they're the same thing actually. So when you model it as a perfect E boundary condition, which okay, it's better if I just draw it. How should I hide this bar here? Hide the floating control panel. Yeah, this is better. Yeah, sorry for that causing confusion. This is the second example I want to show.
Yeah, by the way, there's an answer on this question from the chat. Meissner effect cannot be modeled with HFSS. Instead, London equations has to be solved. Yeah, I think that is true. So I think in HFSS generally it's sufficient. We just model that with perfect E boundary condition. That serves for the most of the purposes for concerning microwave simulations. I think the big difference is in DC. A perfect conductor will allow DC magnetic field, but a superconductor will not allow. So there is a difference in DC. But if we only care about microwave frequency responses, then it's pretty much equivalent.
Yeah, thanks. Yeah. So if I go to the second example, that I want to show you an example of the driven simulation or the response simulation that I want to try with, say, a coaxial transmission line. So the coaxial transmission line is like, it has an outer conductor and an inner conductor, right? So now if we simulate, we assume the outer conductor is a superconductor, let's say a perfect E conductor. And the inner conductor, we can model it as brass, let's say, or copper. We do this. Then the way we create this hollow cylinder is first we create a cylinder. Again, we can parameterize everything. So radius, I call it R outer, or what, radius outer. Okay, again, the reason I have these parameters here is because this job is copied from a previous job that I already make. So we have these parameters already. But if you are making it from scratch, then you won't have these things popping up. So you need to define all the variables yourself. But now I'm just going to be lazy and do it this way. So length or what do I name it? Yeah, these are the variables that I have already defined in this job. So we can call this radius outer, and the length being TL length or transmission length. Yeah, when I do this, it first makes this cylinder, and then with default material assigned as vacuum, of course. And now we want to make another cylinder, just copy and paste it. Now I assign the material to be copper. I think we need to say copper. Yeah. Yeah. Okay. You'll see HFSS have a lot of material stored in its library, and we're definitely not making use of all of them. So But this cylinder should be modeling the inner conductor, which looks like this. So it's a thinner cylinder inside the outer one, right? But now we need to think, so the vacuum or this dielectric is should be the volume filling between this inner one and the outer one, instead of just the cylinder. So what it should be is actually this subtract this should be the dielectric. And there's in the design panel, there is an option in here that unite and subtract. So this is another very commonly used tool in the design. And there's a trick in this that I can do, check this box, this option called clone the tool object before operation. Then what we'll do is after this subtraction, now you can see that, okay, it's not very easy to see here. You can see it from by the way, what I just did is if you in HFS software, if you middle button on your mouse, you just drag it, drag the mouse, see actually it does. But an easier way to see this is view, apply orientation, and I want a top view, which is orientation towards -z, and this is this way. So this is when you have very complicated design, this is a good way to see the actual design. So now the vacuum is actually this object. That's the area filling between the outer and the inner by subtracting the inner from the outer cylinder. Well, when we do the clone option, when we do the subtraction, what it does is still keep the inner cylinder here as the original set. So just make a duplicate of that to be subtracted from in this operation. And the advantage of this is now if you, so remember we have parameterized the inner design like this. So now if you change these, just change the parameter, it actually automatically updates both this inner cylinder and the subtraction. Well, if you don't do this clone from, or if you just do subtraction from like a new object, then you'll need to make sure you manually type in these radius that get updated along with the inner parameter or whatever. So now I know from some analyses, I happen to know that when the outer and inner radius have a ratio of 2.3 for dielectric, for permittivity of 1, which is vacuum, this should give us 50 ohm and 50 ohm characteristic impedance of the transmission line. So when it's a 50 ohm transmission line, and if both of the ports on this end and this end are a 50 ohm ports, then we have no reflection, perfect transmission in that sense. And now in this driven model network simulation, another important thing to do is to set the port or the excitation. And for coaxial transmission line, the port or the excitation should exist on this surface that is pointing from the inner conductor to the outer conductor. That's the E field excitation, right? And the way to do that is there's another trick by selecting, okay, we can do selection mode, edge. And this selection mode is select only the edge instead of object. Now I select these two circles and I say create object, or I think I can do it here. Create object from. Now you make two lines. I can merge them. Yeah, I apologize. Sometimes it's hard to explain everything in here, and I'm afraid you'll have to just watch me do it or follow me do these. So unfortunately, you might be making the same mistakes I'm making. So again, I don't consider myself expert of HFSS, but I'm just showing you the common way I do things. And that doesn't mean this is the one correct way to do things. And I'm sure there's a lot of things that you can do better than me. So you should always practice, play with more things, and find your own comfortable way of using HFSS. But this is a useful tool that I think it's worth spreading. It's what I did is I made this object, which is 2 lines, 2 circles created from the edge of these cylinders. And now we can do create objects from. Okay, now I'm confused. Okay. It's not create object from. It should be the cover face. But why it doesn't allow me to do that? It's in edit, surface, cover line. That's it. Okay, this is embarrassing again. Apparently, I've done something wrong. Just let me do the things again to make sure I get it correct. I create these 2 edges, create object. I can merge them. So I'd make 1 object formed by 2 lines. And now if I do surface, cover line. I'm a little confused. Why is it not creating the things in between? Because I thought that's what we
if you
should
have
do.
if you have an already drawn geometry, maybe you can just go from there.
Yeah,
I'm looking at the time.
I'm planning to go here. So
yeah, seems like we may want to move along towards the quantum part, and yeah, I'm sure some level of details maybe the users can just recheck this video or figure some things on their own.
Yeah, I realize that. Thanks for keeping track of the time. So this is what I was trying to do. Is I want to make a surface that looks like this. And we set the boundary condition as excitation by here. So assign excitation port. And for this thing, I do a lumped port, which is an excitation created with, say, yeah, that looks like this. So in creating a lumped port, another trick is you need to define an integration line that in our case is pointing from the inner surface to the outer surface. But okay, these are all details that you should be able to figure out from all the instructions afterwards. And I'm sorry for not keeping track of the time, but this is essentially what I want to show you, that in a Druid model simulation, it should keep a scattering parameter versus the frequency scan that gives between the 2 parts. So S11 stands for reflection and S21 stands for transmission. So, but yeah, I agree. These are all details of the softwares. So I apologize for this part taking way too much time. But I think it's more important and more valuable to go to the, wait, am I still sharing the, oh my God.
So we are seeing Windows like a pop-up menu and your remote desktop. Well,
okay.
Yeah.
I think it's because I've hidden that toolbar from Zoom. Now I don't know how should I.
If you're trying to get back to your slides, maybe the good thing to do is to stop your remote desktoping first, and then maybe you just hit on escape button on your computer, and that probably get out of the full screen mode.
Okay, I see. Yeah, thanks. That's very helpful. Yeah. So now we should be seeing the slides, right? I hope. Yeah. So, okay, I've spent way too much time on just discussing the classical part of HFSS, but now let's move to the quantum part. Unfortunately, I might need to go a little fast in this demonstration, but at least I want to get the idea correct about what we are going to get from HFSS and what we do specifically with Josephson junctions. So if you remember the story, what we want is essentially the Hamiltonian. And what we have been simulating is just classical electromagnetic environments, which we can say that is for any LC circuit, or can be used to model any linear lossless electromagnetic environments. And we can say for such a system, the Hamiltonian would eventually all look the same, which is like this. Because for any LC circuit, LC network, you can always find the n eigenmodes of the system, and then they are isolated individual eigenmodes, each of them being a harmonic oscillator. And the overall Hamiltonian should just be this, where omega n being the frequencies of each eigenmode. So the only interesting thing and tricky things happen with the Josephson junction. Is when we have the Josephson junction, a junction is essentially a cosine potential. So it actually the overall Hamiltonian should look like this. Have the n eigenmodes as you will get. So when you treat the junction as a linear inductance, then it gets back to the LC circuit that gives you the n eigenmodes. But on top of that, the junction is providing the nonlinear potential that is linear inductance, which now we model as the cosine potential plus the phi square over 2, which is the linear part of that. So the reason we are taking the linear part of the potential, the quadratic part of the potential out from the cosine is because we want to include that in the linear eigenmode, right? So these are the modes that gives you the qubit frequency, which is given by Lj of the junction, which comes from the quadratic part of its potential. And we want the nonlinearity to capture whatever is on top of that quadratic potential. So the idea behind this is when we have a junction seeing a linear environment, we take the linear part of the junction, which we can model as a L and C, etc. We combine this linear part of the junction along with the rest of the environment as one black box, that is one response function. And we want this, so whatever in this parentheses, cosine taken away the quadratic potential is modeled by this spider component, which is just the nonlinearity of the junction. So there's okay, I might want to skip this part if it's taking a bit too much time, but the basic idea of this so-called black box treatment of electrical circuit is a theorem called Foster theorem, which basically says the reactance of the imaginary part of its impedance of a passive lossless one-part network can be modeled as a circuit like this.
Just a saying, we do have like 1 extra hour that we can use set aside for this class. So you don't have to rush or anything.
I understand.
Make sure I explain your material.
But I want to leave a few times for the for that demo job with the junction simulation. So, so I think the exact formulation of Foster's theorem is not really of interest. So what we usually want from it is the Foster decomposition, which is kind of the equivalent circuit of any passive lossless one-part linear network. And what it does basically is it captures so each LC oscillator captures a pole in the response function that look like this. So, and there's this capacitance that captures the pole at 0. So when you have a pole at 0, infinite impedance at 0, it's modeled as a capacitance. And when you have an infinite impedance at infinity, It's modeled by this inductance. And then you have all the eigenmodes at finite frequency, which actually in the Fourier domain, you should have pairs of eigenmodes at plus omega n and minus omega n, which are captured by these LC, so parallel LC oscillators. So with this Foster decomposition of any passive lossless two-terminal network, that we can now think of this network as whatever linear environment seen by the Josephson junction, which in our case can be a junction seeing two paths and then enveloped in a 3D cavity, etc. So I envelope everything else apart from the junction into that linear environment. And now I consider the linear inductance of the junction and pack it along with that linear environment and do a Foster equivalent circuit treatment of this whole dash box. So this is the new black box that we consider, the nonlinearity of the junction, these. So I write it this way. I kind of just neglected these two, and that's a common thing to do, because if you think of it, a junction has, so these two terminal on the junction has, at DC, it's actually a short because there's a junction LJ inductance on it. So it doesn't have a pole at DC, and it doesn't have, it kind of, since the junction always have the parasitic capacitance, we can say at infinity, it always has, it's a short as well due to the parasitic capacitance. So usually in a lot of cases, these series L and C are negligible in the Foster circuit decomposition. And this is what you will find actually in most of the reference. But so in this case, we can actually evaluate what this phi that appears in the cosine potential is. When you do the Foster circuit decomposition, you'll find that due to current conservation or Kirchhoff law, that this phi that the junction sees, or when we write it this way, this phi that goes into the nonlinear potential is essentially just the phi of all the eigenmodes, all the LCs, and the sum of these should constitute this phi. So this is basically what we call the black box quantization method, which is we treat whatever linear parts into a black box that we find the eigenmodes that corresponds to this LCs. And then we do the quantization from putting that phi into a cosine potential and add hats or make them operators afterwards. So these eigenmodes are what we extract from HFSS. Well, another thing we want is how to express this phi in terms of the eigenmodes operators. So for that, as I just said, phi is just the sum of all of these phi's for each eigenmode with a prefactor phi ZPS that stands for 0-point fluctuation for each eigenmode. So the first task is to get all the eigenmode frequencies omega n, which we already know what to do. We already know how to do. The second task is to get how all of these phi ZPS for each of the eigenmodes. And there are two different methods to do that. The first one, as in this original reference for black box quantization, I call it the response method, which is basically you can simulate the response seen by the Josephson junction in HFSS. Like you can simulate this Z of omega exactly, and you'll be able to extract these KNs from that response function. So in the way we write it, Kn is just the pole or the residual of this impedance function at these frequencies separately. Or you can simulate the admittance function and get the derivative at these resonance frequency to get that Kn. So Kn essentially give you L and C values for each of the mode. So the L and C values give rise to the eigenmode frequency of this mode and the impedance of this mode. And that impedance is directly related to the phi ZPF. So when you know that, we can construct the overall phi parameter from the phi ZPF of each mode. I probably have gone too fast in this part. So I hope you have understood at least the basic idea of what we're trying to do. So this treatment is a little tricky, and it doesn't matter because this is not the most commonly used method nowadays. But I hope you at least get what I mean by what we're trying to do is to compose this phi operator in terms of the eigenmode. And what we want is these three factors, right? So we can either do it from the linear response method, or we can do it with another method, a more popular and I would say more commonly used method nowadays, that is called the energy participation method. So the idea behind the energy participation ratio method is, if you think of it, so if you look at this Foster equivalent circuit at 0 frequency, at DC, then the overall, so all the capacitances are like open at DC. Then all you see is the sum of all these inductances, right? And we know what that sum should be, because the junction, across the two terminals of the junction, the overall inductance or the response at DC should just be the LJ, just be the Josephson inductance of the junction itself. And this allows us to consider the energy, the inductive energy stored in each of the mode in terms of how much of that is, so how much of the junction participates in each of the modes from fraction of the inductance participation. So, and this, it's possible to extract that ratio from HFSS as well, because for each of the eigenmode, there's always the conservation law. There's always the, I think, equal partition of energy, that the inductive energy and the capacitive energy should equal to each other. Or put it this way, the energy stored in E field and the energy stored in B field, magnetic field, is always equal to each other. Now, there is such a lumped inductive element, which is the junction, but there's no such lumped capacitance in the network. So all the capacitive energy, all the electric field energy are just distributed in the whole geometry. So we're always able to extract that overall energy from integrating the inductive energy. Sorry, we should say integrating the capacitive energy or integrating the E field square over all the entire geometry. And we can calculate the inductive energy stored in the junction by integrating the current flowing through the junction. And the ratio between these two should give us the energy participation, which is a value that we can extract from HFSS directly. So these two, again, from HFSS, we can extract this value. And from the Foster circuit decomposition, we should tell this value as like the effective inductance for each mode versus the LJ. And that give us phi ZPF in this form. So this is how we would evaluate phi ZPF from that participation ratio, and we're able to extract the participation ratio from HFSS. And that's the basic idea of this energy participation ratio method to applied in black box quantization. So again, I apologize. I know this part is not made very clear, but just to make a comparison between these two methods that I talked about. So in practice, what we want to do is to get the eigenmode frequencies, again, to get the eigenmode frequencies omega n, and to get these phi ZPS for each of the eigenmode. So we can either do it from driven model simulation in HFSS, that we want to sweep the frequency across each eigenmode, and then from export the linear response function, either the inductance or the admittance matrix, and evaluate these values to get phi ZPF. Or we can do an eigenmode simulation in HFSS and evaluate the field, so calculate the E field energy in the whole geometry and the current, integrate the current flowing through the junction to extract the participation ratio, and then use these to evaluate phi ZPF. So the difference lies in whether you think running a driven model simulation in HFSS versus running an eigenmode simulation in HFSS, which is more preferable. And I would say, of course, running one eigenmode simulation is much simpler than running like several driven model simulation that sweep across each eigenmode. But the tricky part in this EPR is that you need to do this field integration and extract the participation ratio. And that is not a trivial job. But fortunately, there is this Python package called PyEPR that Zlatko wrote. So because of the existence of this package, now the energy participation ratio method is a more popular method, I would say, when people actually do the black box quantization. So
wait, there are a couple of questions. One is that how do you do this with more than one junction or spider? Are you going to cover that?
I am not. Because next I want to go into that example, but all of these are, you can find it in this original black box quantization paper and also in Zlatko's paper. And I think the PyEPR package has a very detailed documentation on these treatment on multi-junction. So
do you want to just comment very briefly on the general idea of how to treat multiple junctions?
Yeah. Thanks. So here I kind of already write it this way. Okay, if we go here, I already write it this way, that each junction is giving us a cosine potential, and the phase drop across each junction is different, right? So basically, the job when you have more than one junction is we want to write down the participation of each junction in all the modes, and we decompose the phi m. So here the m stands for number of junctions. We want to decompose phi across every junction in terms of the sum of operators of each eigenmode. So that can also be done with either the linear response or energy participation.
Yeah, another perhaps a more complicated question is, can you account for external flux in this model?
Good point. It would be very complicated to accommodate for time-dependent flux. But when we have, say, any Josephson dipole, a Josephson loop that involves a static flux, that we can always write the overall potential as a function of phase drop across the junction. If the external flux is a static flux, then that flux just goes in as parameter in the potential energy, right? So whenever we have a Josephson dipole that you can write the overall potential function of, then these EPR methods still apply. But yeah, when you have external flux that is dynamical, that is time dependent, then it is indeed very complicated to accommodate for. And there are several ongoing works on that, but I think that's really beyond the scope of this tutorial.
Okay, so can you give some typical idea of common values of the EPR, these energy participation ratio, coming out of your simulations?
Yeah,
for
so
a typical qubit cavity system,
which is what I'm planning to show you next. In basically, when you think of a 3D drum, that almost most of the inductance come from the junction LJ itself, right? So, which is to say, for the qubit mode, the resonance mode at qubit frequency, the participation of the junction should be close to 1. And then that participation for like when you have a readout resonator, the readout resonator has cross curve or has this dispersive interaction with the qubit mode because of the readout mode actually excites the junction, induce phase drop across the junction as well and sees the nonlinearity. And that participation is usually very small, it's sub 1% or sub 0.1% even. So yeah.
Thanks.
Because that's a good question. So if you think of it, that participation actually goes into phi ZPF directly, and so phi ZPF square essentially gives you the scale with the anharmonicity of that mode. So that anharmonicity of the junction itself is very large, but anharmonicity of the cavity mode, we usually neglect that. So because the participation is very small. So yeah. And up to now, I've only talked about linear lossless circuit, but in the actual experiment where you want to include loss as well, then what we usually do is this so-called lossy Foster decomposition, which is actually not an exactly correct thing to do, because the Foster theorem actually does not apply when you have lossy response function, but we kind of do it this way when all the modes of interest are high Q. And high Q means when they're the separation in Laplace domain are dominant by the separation along the imaginary axis. Well, when the real part of the eigenmode in here that characterize the loss constant of the modes are much smaller compared to the separation of the modes on the frequency axis. But a more exact, so in that high Q approximation, and you need all the modes to be high Q. In that approximation, we can kind of approximate the lossy circuit by this LCR circuit instead of just LC circuit from Foster. But the exact treatment of a lossy circuit would be something called the Brunner circuit, which is actually introduced in detail in this article. But I think, again, that's a very complicated thing. And I'm just showing this reference here in case you're interested, but I'm not going to go into detail for that. So now for the rest of the talk, show you an example of a cavity coupling to a transmon coupled to a readout resonator. So this is a typical, we call 3D transmon architecture. So I'm going to show you how it looks like in HFSS and how do we model these things, and how do we model the junction, and how do we use PyEPR to call that solution to evaluate the Hamiltonian. So just again, several basic ideas before we go into HFSS. I want you to understand what these cavities I'm going to make are and how do they look like. So the first cavity I want to include is a storage cavity that usually we use this cavity to, we use the junction at and sila to manipulate the bosonic field of this cavity. And the requirement for this 3D cavity is usually we want it to be as high Q as possible. So this is where these so-called stub cavity come into play. And the reason these cavities has relatively higher Q than other 3D cavities, say rectangular box cavity, is because this thing is in principle seamless. It doesn't have seam. So this whole thing is machined as one piece, and they only have one opening from the top. And this top, so from most of the E field is confined in here as the λ/4 coaxial transmission line, basically, that has E field structure like this, shorted here and like close to opening here. And the seam exists here, which is physically far away from the E field. And there's an exponential decay of the E field due to this tunnel cutoff frequency. So that's why usually the seam loss is negligible, or not really negligible, but we can mitigate the seam loss for these 3D cavity to make it high Q. So this is one very common tool or very common design in 3D transmon architecture. And then we can couple to this storage cavity by a transmon from a chip that is inserted from the side, and then introduce another low Q cavity to do readouts on the qubit. And that readout cavity, or readout resonator, we should say, it's not really a physical cavity. It's a strip line made on the same chip of the transmon that looks like this, which is introduced in this article. Actually, this is a good article. I suggest you go take a look at. So these are some of the very common building blocks that we use in 3D transmon architecture. So this strip line resonator, sometimes called coax line. So it's a combination of coaxial and microstrip, strip line, basically. So it's also kind of you can think of it as a transmission line, as the center conductor here, while the ground is provided by the tunnel, or the outer conductor as the tunnel itself. So when you make a strip line here, it forms an λ/2 standing mode. And this we can make it low Q by coupling it strongly from external ports and read the transmon from this resonator. So I hope you have a basic idea at least about the geometries we're going to make. And now, if that's the case, I'll go to the remote desktop again to show you this example. Okay. Again, this is how the geometry should look like eventually. That's the 3D post cavity with a transmon fabricated here that has capacitive coupling to this, the first stub cavity, this coaxial lambda/4, and has a capacitive coupling to this, like lambda/2 strip line. So, but I think I can skip the actual modeling of like this stub cavity. The way I make this is, again, as you can see, it's a cylinder subtract another cylinder that is this, so the center stub, and can make the cavity of this thing. So maybe before I simulate this whole structure, let me just show you a quick example of how the field looks like for the stub cavity. Okay. Yeah, so hide inactive view. It's another very common practice to plot the field just to look at the E-field structure of a resonance mode. This is a stub cavity that I have done eigenmode simulation. I simulated 5 modes again, and if you look at the results, it has a standing mode at say 4.5 gigahertz. And if I want to look at how the E-field of that mode look like, I can select the object, say plot field in. Then the E-field of the base mode look like this. So in the field overlay, you can edit source. And this allows you to say, I want to see the first mode, mode 1, or mode 2, mode 3, mode 4. So you can adjust the amplitude of these eigenmode structure that you want to plot. So this is if I plot the second mode, which is something at 14 gigahertz already, then it looks like this. But now if I just want to look at the first eigenmode, then I expect it to have roughly a lambda/4 field structure, where the E field should be strongest at the end of this stub and 0 at here, while it has exponential decreasing along this cutoff where it is true. So this is the E field level in BB level. So when you have an idea of what this stub cavity field structure should look like, now we can couple to this stub cavity by the dipole moment that looks like this. So I want to show you how I model the transmon and the 2D strip line actually in here. So this is a final job, but I can show you. Okay, maybe it's. This is a job I made. The stub cavity along with the tunnel that I insert the chip from. And now another common, a handy tool to use in the design is this so-called relative coordinate. So you can define structures in, for example, where I put the sapphire chip. I define the position in a coordinate that I define myself. So tunnel end is a coordinate that is here. So I can define the position of the chip in here. So with respect to this coordinate. And the advantage of using relative coordinate is this allows you to change all the geometries, again, by changing, say, one parameter. Saying here, I want to adjust the post length or this stub length into 20 instead of 15 millimeter. Then, yeah, it basically shifts everything with respect to like a fixed relative position to this stub if you define the relative coordinates in a smart way. But okay, that's a minor trick. But now I want to define everything within a relative coordinate that is the chip edge. Say here. We can model the 2D structures by, sorry, let me just hide these thing again. We can model 2D surface in the same way as we create 3D objects, just in here, sheet. We model the transmon as, say, two pads with a lumped inductance in between. So the two pads of the junction, we can say pad X, pad Y. We define its position as, this is making it centered. Okay, you can say distance. Where here, as you can see, so the pad X and Y determines the X and Y dimension of this sheet. And then the distance transmon is the distance between the edge of the pad to the 0 in this coordinate, which is now the edge of the chip. So this is how I would model the pad of the junction. And just for, in order to see it more clearly in HFSS, you can change the color of this object, where I usually prefer to use red for these 2D structure, etc. So just as a demonstration, so I'm not going to make the whole structure for you. This is a good practice. You can do it yourself. Well, some of the important things to watch out is the meshing for these 2D surfaces. So we want to mesh the 2D surface much finer than we do for the 3D rectangular cavity, of course. And this transmon, for example, it has a pad of several hundred microns by itself, so 600 micron by 600 micron. And usually for the transmon, we want the mesh to be smaller than, much smaller than this dimension. And more importantly, we want the mesh to be fine on the edge of the feature. Because for a 2D superconductor, usually the E field is denser on the edge. And we want the initial mesh to be able to capture that dense region of the E field. Because as I said, so HFSS only converge from run to run. And if the initial mesh already misses some charging effect on the edge, etc., then it might converge to a wrong value. So it can converge to, you can say, a local minimum without even capturing some edge charging effect. So in order for that to not happen, we want the meshing to be fine enough to capture these sensitive charging effect on the edge. But it might be very, very expensive to mesh the whole thing to that precision. So a handy trick I do is I mesh differently on the edge versus on in the bulk of the 2D superconductor. And this is done by, so I create two objects, one as the bulk of the superconductor, like, I shouldn't say the bulk, like the inner area of this sheet, and I create a separate object for the edge of this object. So we can do want to do this copy, and can I do? I think I need to select the edge of one 2D surface. And then there's this option called move edge, which means now I create a new object, or I make this object that is moving 20 micron inwards from this object, from the edge of this object that I just draw. When I do this, come on. Yeah, the new object looks like this, actually. It's everything shrinked inwards by 20 micron. And then I can do the same trick at subtract. So this making an individual element that is just the edge. So in this way, I can mesh this thing on selection, lens-based. I want the edge to be meshed by no more than 20 micron large in the mesh size. And the inside of this thing is a much larger bulk that I can ask this to be, say, 100 or 150 micron meshing. So both of these two objects is physically the pad of the transmon. So they should have a boundary condition as perfect E, which is 2D superconductor. Yeah, and it has all these the different mesh operations that I applied just now. That it meshes differently on the edge and the inside. So you do the trick on every 2D material we do, and then this is how we generate the overall plots that look like this. Okay, again, I'll view it from the top. Then this is the how the it look like. It has these lead from the pad to so these are the pads that we just made, and the second pad, and they're a tiny superconducting layer I call the lead that leads to the junction, and finally the junction part. I usually model the junction as just a small rectangle sheet that say looks like this. So the shape of the junction doesn't really matter, because what it does is basically we assign a boundary condition called the lumped RLC. Okay, I don't want to edit on this object. Maybe let's go to that practice object and make another sheet in here. Again, we want to parameterize the junction, etc. But the important point here is I want to show you the boundary condition of lumped RLC, where I call it Josephson junction. It's this element. And the junction has a boundary condition that is LJ. What? Okay, I see. Yeah, LJ is a predefined variable that I have defined in the project. So the reason it failed to create this object just now is because I haven't defined the current flow line. This is something we need to define for any lumped boundary condition or lumped port that is basically asking HFS to evaluate the field for along this line. So now we define it this way. So what this element does in HFSS is now it effectively serves as an LJ, which in the value we set to be 10 nanohenry, for example, from this point to this point. And since it's so small an element, lumped means the geometry of this element should be much smaller than the wavelength we care about. So basically, this is as from this surface to this surface, from this edge to this edge, has an effective boundary condition that is given a phase drop, a response function that is described by an LJ. So where we can parameterize all these inductance values as well by the same method here. So this is how we would model the junction, and as you see here. So some people might model the junction as just one one long rectangle that goes from this end to this end, which should capture it like basically equally fine, but I think that's a minor detail. So yeah, this is what I want to show you in the design part. So same trick applies to the cavity, shouldn't call it cavity, resonator. That again, I create a new object on the edge and mesh it finely here. So one last thing to mention is this rounding on the cornering here. So the reason I do this is this is a common trick applied in transmon design. It's because we see that the transmon lifetime is mostly limited by dielectric loss from the surface. And the dielectric loss on the surface is worse at the points where E field is densest. So we don't want anything like sharp corner, like right angle corner, because it will have very dense E fields at there. So it'll probably help with your transmon lifetime from dielectric loss by rounding all these surfaces. And this is very easy to do in the design by just generating, say, we can select this element and pick a vertex, which is this, and do the fillet from here. So we can define the fillet to be, say, 50 micron, and then it'll do this. And we should, if you do this before we do the clone and duplicate and do this edging, then it will hold the whole surface, or the edge elements also have the same fillet that looks like this. So this is a job I have created, and no worry, I'll share this file with you, and you can play with it afterwards to actually run the simulation. And I would recommend you duplicate this design to just adjust some parameters to see how the eigenmodes look like. And now, if we have set the mesh, set all the boundary condition, and actually ran the simulation in the analysis. Now we're able to see the eigenmode results from this simulation. Oh, okay, maybe not this one then. Is it this one? Yeah, I think so. This is the one that I have ran before. So we don't want to see the mesh now. We can disable these mesh views. And now it's plotting the field structure. So it's showing the first mode. It's showing the second mode, which is the qubit mode, I believe. And let's see how the qubit mode E field structure looks like. Yeah, so this is the second eigenmode of the system that it has simulated. It's a eigenmode at 5.3 gigahertz. And you can see the E field structure is very localized, confined around the junctions, around the qubit paths. So yeah, the E field is mostly here. So that's how we confirm that which mode is which. This is the qubit mode. Of course, when you make the design, you should have a rough idea of what frequencies I want these modes to be. So instead, now if we plot that field structure for the third mode, that I expect to be this readout mode, which should have a structure of lambda over 2, which is E field strongest on these two ends. And that looks like this. So just to confirm, the third mode is the readout mode that I targeted at around 9 gigahertz, which is from this on-chip strip line. And besides, so here, I'm only viewing the frequencies of the modes, because that's what in the eigenmode simulation it converges on. But it actually, HFSS stores more than that information. It stores the entire field of these modes in the solution that it saves. And that field is what PyEPR calls to evaluate the participation ratio. I'm not planning to go through the codes with you, but this is run. So the PyEPR package, again, has very well documented, has a very well-written document that I recommend you go through. But usually the way we use it is you write like a batch code like this for yourself, that you define a project info of the path of your HFSS file and the project name, design name, which in our case, the project name is this, tutorial 3D transmon. And the design name is, it's this, cavity cav transmon RO. So this is the things we type in this batch code that calls PyEPR. What it does is it creates, so you need to specify the junction object that it does integration. So it integrates the current flow on this object, which is junction 1. That is this object, JJ. So rectangle JJ, you define it here. And the integration line for the Josephson junction that I define separately. Oh. I don't want to see the mesh now. So this is the junction element and a line that is just duplicating the integration line of that boundary condition, which I define separately as in here. So PyEPR calls that as well. And you need to provide the LJ value for it to evaluate the effective, like basically EJ for it to evaluate the nonlinear potential of this thing that it stores as one element in a dictionary called junction 1, called junction, that I named junction 1 in here. So let me just try to run this code and see if it calls the result properly. So the first thing it does, the first half of the job, is it exports the solution from HFSS and say, it knows that I'm simulating for 5 eigenmodes, and the first mode is 4.58 gigahertz, and it's calculating the energy of the overall magnetic field, and then evaluates energy participation ratio from that. So the electric field energy, and I think this magnetic field energy as well, is calculated from just integrating the field over the entire object. Now it's getting slow. Yeah. Okay, so it's doing it for all the modes now. And the second half of the code is doing the Hamiltonian analysis. So this part would save the participation ratio, etc., into an MPZ file. And the second half is doing the EPR analysis, which is from the energy participation ratio to extract to add in the nonlinearity and to make everything into operators, Q-tip objects, and do the Hamiltonian analysis. So in that part, I ask it for analyze all variations, which so variations in this case stands for if I change some geometry parameter, then if I'm sweeping some parameters in HFSS, then it is able to analyze all of them to see how the final result depends on certain parameter in HFSS. But in our case, we have only one variation in here. And then in the setup of the eigenmode simulation, I have included 5 eigenmodes, but I only want the Hamiltonian or the chi matrix that includes only the first 3 modes. So 0, 1, and 2. And this is where I define it. And I define a truncation for that cosine expansion, and I define a Hilbert space size for each degree of freedom. Okay, so I say I have 3 modes. Well, each mode I want to include 15 Fock levels, and then this is going to construct the Hamiltonian of the tensor product of these 15 times 15 times 15. So and then it does the so there are 2 ways to extract the final Hamiltonian. Okay, yeah, it's taking a little longer than I expect, but I can walk you through what these are. So this is mode 1 at 5.3 gigahertz, which is the transmon mode, and as expected, the energy participation ratio of the energy is close to 1, 97% here. Yeah, and then there's this mode where at 9 gigahertz, which is the readout resonator mode, and the energy participation ratio of the junction is actually around this much. So that's what 0.1%. So, and same applies to the first mode, which is the stop cavity mode. It has an energy participation ratio of the junction of also 0.16% roughly. So from all these values, now it has done the first part. It saves all the EPR of the eigenmodes and then start doing constructing the Hamiltonian defined here, and then numerically diagonalize the Hamiltonian. So, which just want to show you how the final result look like. Good. So it gives you the corrected eigenmode frequency that accounted for the lamp shift when you include the quantum mechanical correction. And then this is usually the result we want from this EPR analysis. So it's something we call the chi matrix, where the diagonal elements give you the cross curve of each eigenmode. So the first mode is mode 0, is the storage cavity mode, which is almost a harmonic oscillator. It has a barely negligible self curve. That is self curve of, I think, 1 kilohertz in this case. And then the transmon has the self curve of 170 megahertz. The readout cavity has a self curve of this much. And then the cross element gives us the cross curve between the transmon and these modes. So it has 1 megahertz cross curve currently. And now you may realize there are 2 blocks of these. The first one is called the PT, which stands for perturbation method. So this cross curve matrix is generated from perturbation treatment of the cosine potential on top of the linear eigenmode Hamiltonian. So it treats the linear eigenmodes. Okay, it might be easier to go to the slides now, but okay, again, it treats the linear eigenmodes that are 3 individual omega n a dagger a as the static Hamiltonian, and treat this cosine term on top of it as the perturbation. So this is how it gets the perturbative chi matrix. But these deviates quite a lot from the numerical diagonalization, apparently. So most of the time, we consider the numerical diagonalization of the Hamiltonian to be more accurate, to be more reliable. But it's always a good point to make these 2 matches to some sense. Like now, it's not so. When this is giving me like a 0.4 megahertz stock shift, while diagonalization is giving me a 1 megahertz, I don't know either of these are trustworthy or not. So that might be due to the truncation of my Hilbert space size being too small. So sometimes you need to include a larger Hilbert space size to get the perturbation method to be more precise, etc. But just due to the sake of time, I'm not playing with that now. But this is something you can try when you're actually doing the EPR analysis to see when you vary these. Again, you should at least expect the this pi EPR calculation to give you a result that is not very sensitive to your truncation, for example. So yeah. So I would like to go back to the slides. This is basically all I want to show you in the talk. So I apologize if a lot of the things is not very clear. And again, I'm not showing you the one correct way to do HFSS analysis and PyEPR. A lot of the things I do is probably not optimized, and you can definitely do it better than me. But just these are some key points that I wanted to talk about in the HFSS design that I might have covered or not. But I'm going to leave these points here and share this slide with you. When you are working with HFSS, you can go back to look whether you are paying attention to these things that I think was worth paying attention to or not. The last thing I want to talk about before I wrap up is what I've been showing you is how to manually generate a CAD design in HFSS. But in a lot of cases, it might be easier to use some typing tool, to use some software that generates that for you. So especially when you are dealing with complicated 2D circuits like this. And IBM has this Qiskit Metal package that does exactly that. So it's a very self-explanatory package. It has very good documents again. So I really recommend you to go take a look at their package. And Qiskit Metal is, again, not the only thing that does this. There's another package called HFSS DrawPy from a French group that basically does the same thing as Qiskit Metal, that you can parameterize the things in Python. It has a GUI of itself, and it generates the HFSS design for you, basically. But again, it kind of generates the design inside HFSS because HFSS doesn't like you import things from external. So maybe when you are making this kind of design and you want to do a full EM simulation, it's better you make this design either via these softwares or you modify some things by hand in HFSS and then export this as a GDS file for your fabrication. Yeah. A last thing is, yeah, maybe so just a quick comment on that. So I mentioned that energy participation ratio is calculated in HFSS from this field calculator. And if you want to do something more complicated than the PyEPR package automates for you, you can define what you want to evaluate in here by yourself. So this is like magnitude E times that gives E squared integrated over volume this that gives the overall E field energy within this cylinder, within this object. But the syntax of this thing is a little I'll say not very intuitive. It's something called a reverse Polish notation. But yeah, I think this is really is required for this class. So if you want, there are more reference on these stuff on HFSS that I can share with you. So yeah, end of the talk is I hope you still remember the overall goal we want to do with HFSS and PyEPR is we want to test whether a design give us our target Hamiltonian or not. And usually the Hamiltonian we want is just a dispersive Hamiltonian with the n-harmonicity of the transmon and cross curves between the transmon and any modes, etc. So this is what I have shown you is generally designing HFSS simulated PyEPR package to evaluate that. And if that gives you the parameters like chi's and n-harmonicities that roughly as you need in your experiment, then it's good. You go to the next step, or you just go back to modify the design to simulate it. So that's the place of basically this lecture in the overall workflow that I hope, even if you don't remember anything else from the lecture, I just hope picture or at least the goal of what we're doing with HFSS stays in your mind. So either if you're doing it yourself, it's always a good idea to keep track of what I am doing. So I'm making the CAD design or I'm doing the electromagnetic meshing. And what is my goal? It's always good to keep that in your mind. Or if you're not doing that yourself, it's always good to know what experimentalists do to get this done. So yeah, that's the end of the lecture. Thank you, guys.
Oh yeah, thank you very much, Wei, for the very detailed description of the whole workflow.
Yeah.
So Yeah. Your camera seems like having a huge like a purple background on it. I was just wondering if you can you can try anything. I'm not sure if what you see on your side, but it seems like you're basked in the purple shade.
Oh my
Okay,
God.
okay, now it's good.
No, it's better. Yeah.
Yeah. So we can take some more questions for a few minutes if you guys want to type in anything. And there's a couple like a couple quick questions. One is, do you know if you can run PyEPR on Linux?
I don't. The honest answer is I don't. Yeah.
Yeah.
Yeah, I haven't done that. So
Yeah.
that's a question for Znako, actually. So
Okay. Yeah. So a question on slide very beginning of the talk. So you mentioned a few 2.5D softwares. Do you happen to know if they can handle flip chip simulation or just like for single layer, like a planar type of chip?
yeah, as far as I know, what 2.5D means, it is it can handle such flip chip and through chip via stuff that yeah. So I think 2.5D, by what I mean by 2.5D is multiple 2D surface with the interlayer connections. And both of these two softwares can handle that, actually, Axiom and Sonnet.
Yeah, so here's a good question. So we learned about SC qubits last class. So what's the relationship between SC qubits and this PyEPR scheme? And when do you use SC qubits and when do you use HFSS?
Very good point. So in some sense, SC qubit and this HFSS plus PyEPR are doing the same thing. We want to do the same thing, is to synthesize a Hamiltonian. You start from a LCJ circuit, or you start with a distributed element circuit, which is like the geometry of the whole thing. So sometimes it's possible to actually design the circuit in this way, especially when you're doing 2D and most of the stuff being quasi-lumped elements. So, and that's the point, you can start everything in SD qubits, which is you parameterize the circuit by giving it L and C values. But in 3D transmon experiment that I do, for example, I don't have an exact LC model for my whole package. So mostly I don't use SD qubit a lot in my design. I kind of just start from HFSS directly. And as you see in the workflow, most of the time, I don't really need to convert the distributed element circuit to an LC to get my desired Hamiltonian. But sometimes you do need that conversion. So I would say it depends on what your goal is. If you just want to get the dispersive Hamiltonian, extract all these parameters, then SC qubit and HFSS plus PyEPR can be sort of two parallel paths to go. But sometimes you want more complicated thing, like I want the exact circuit topology. I want it to generate an effective LC circuit out of a distributed element. Then you need to do more things from instead of just simple PyEPR. So yeah, I hope that is clear, partly answer the question at least.
Yeah, that's good. Actually, there's a related question.
Yeah.
Yeah, do you, I'm not sure if you know the answer, but maybe just let us know. Can you simulate fluxonium or other like more complicated qubits with high anharmonicity using HFSS and PyEPR at all?
Again, that's a good question for Zlatko, the developer of PyEPR package. But yeah, so I don't do that. And as far as I know, the current version of PyEPR probably doesn't do that in a very good way. Maybe it's starting to include that, but I don't think it's a common thing that the current version of PyEPR involves.
Yeah, from my understanding, PyEPR really only just work with this dispersive type of simple oscillator basis perturbation and Hamiltonian. So, well, I guess that may not be exactly accurate. It can be beyond like a simple perturbation expansion a bit.
So we can say
but
there are
it really
So yeah, I was trying to say there are two things that PyPR do. The first is export the things, the result FSS to calculate these participation ratio, etc. And the second part is the Hamiltonian analysis. So the current Hamiltonian analysis part is specified for the low enharmonicity qubits. I guess the first part should apply to Hamiltonian circuits as well. It's just then you need to, from these participation, you need to know how to construct the Hamiltonian yourself, which could be a good add-on to the current PyPR package.
Yes. I agree. Yeah. Okay, so there is a question I haven't really digested yet. So, given these transmount device parameters we derive from the model, such as number of modes and frequencies and the ZPF, can we then just plug those into our quantum Hamiltonian model to simulate quantum dynamics?
I think you can, right? So when you have the parameters from the static Hamiltonian, then you can, of course, construct the Hamiltonian in QTIP and do numeric experiments. So
yeah. So what we're teaching today is about the static Hamiltonian. So how do you draw up the device and achieve a static circuit Hamiltonian? So on top of that, if you want to work with dynamics that involves external drive, so you will need to add drive to this Hamiltonian and to simulate quantum dynamics. Yeah, so there are multiple links to to this process.
Yeah, and maybe I should be more modest in this way to say. So I was saying we test whether it gives us the target Hamiltonian, but actually what we really get is only the parameters in the Hamiltonian. So you need to know what the form of Hamiltonian you start with to run that analysis. So we only extract the parameters in harmonicity, QIS, etc. So if you want a fancy Hamiltonian like 0 pi qubit, then yeah, PyPR doesn't do that for you. So yeah.
Okay, and Wei, you mentioned that you will be happy to share some of the files. Do you have some way of sharing that you've already figured out, or we should discuss and see if we can do that through the center?
Yeah, I don't. We should discuss afterwards, I guess.
Okay,
yeah, but I think it's valuable to distribute this practice job as well, along with some documents. But yeah.
Okay, sure. Yeah, so thank you so much for giving us this fantastic, very practically useful talk.
Thank you, guys.
Yeah, thank you, and thank you everyone for joining this lecture today. Yeah, bye.